This video is about differential equations. It's the first video in our series of videos on differential equations. So I'm going to answer the question, what is a differential equation, or what is the course differential equations about? And what are differential equations themselves? We'll define differential equations, we'll define the solution of a differential equation, and then we'll verify that a function is a solution of a differential equation. Okay, so we're taking differential equations. I always ask my students in class face-to-face, do you even know what this course is about? Do you know what we're trying to do here? Most people know that differential equations is supposed to be hard, and that's about it. But the best way that I can describe it is through a parallel with algebra class. In algebra, you're trying to find x. We're going to pose a problem for you. Usually it's an equation. Maybe it's something like 2x plus 6 equals 0. And your goal is just to find the value of x that makes this true. In differential equations, it's very similar to solving an algebraic equation. I'm going to give you a differential equation, and a differential equation is just an equation containing the derivative of an unknown function of one or more independent variables. So maybe your differential equation looks like this. Maybe you've got y prime equals 3y. Over here, your goal is to find x. And over here, your goal is just to find y. You're trying to find a function y of x that satisfies this differential equation. So you're saying to yourself, okay, what function is out there that I can take the derivative of? That when I take its derivative, I get 3 times the original function back. Well, here's one solution to this differential equation. Y equals e to the 3x will work, because if I take the derivative of e to the 3x, I get 3 times e to the 3x. So that's 3 times the original function. Or if I take this function and I multiply by a constant, I still get 3 times the original function. What's the derivative of a constant times e to the 3x? It's that constant times e to the 3x times the derivative of the insides times that 3. So this satisfies the differential equation. So that's one example of a solution of a differential equation. So let's write that down. We'll say a function that satisfies the differential equation or a function that makes the equation true. On some interval I. And I, with the largest interval I, where that function satisfies the differential equation, is called the maximal interval of existence. So we're saying the largest interval I, where a given solution y of x satisfies the differential equation. So for this one, turns out that this is going to work. It's going to be a solution to the differential equation all the time. So the maximal interval of existence would be all real numbers. Now, if somebody asks you to verify that a function is a solution of a differential equation, it's basically the same as verifying whether an x value is a solution to an algebraic equation. You just say, well, if I say is x equals 1, is that a solution to this equation? One way that you can determine whether x equals 1 works is to just plug it in and then see if you get 0. 2 times 1 is 2. 2 plus 6 is 8. 8 is not equal to 0. So x equals 1 is not a solution of the solution of the algebraic equation. If I want to determine if this function is a solution, all I have to do is the same thing. I just plug it in. I take its derivative, I substitute into the left-hand side, I substitute into the right-hand side, and if the left-hand side equals the right-hand side, then it is a solution of the differential equation. So let's, as our first example, let's verify that y equals c times e to the 3x is a solution of the differential equation y prime equals 3y. Well, first we'll compute y prime. So this is the left-hand side. And I'll use LHS as an abbreviation for left-hand side. Left-hand side is y prime, and we're assuming y is equal to this. So we've got a constant times the derivative of e to the 3x is e to the 3x times the derivative of the inside, which is a 3. So we get 3 times a constant times e to the 3x. The right-hand side is 3 times y. So that's 3 times y, and y is equal to this. So we substitute that in. So on the left, we have 3c times e to the 3x. On the right, we have 3c times e to the 3x. So put those together. Since the left-hand side equals the right-hand side, y equals c times e to the 3x is a solution of the differential equation. And the maximal interval of existence is the largest interval for which this will satisfy this differential equation. And it's always one interval. It's never a union of several intervals. And it's going to be all real numbers. Because it doesn't matter what x is, the left-hand side here is going to equal the right-hand side over there. So this function on this interval is a solution of the differential equation y prime equals 3y. And I'm just abbreviating solution SOOLN. Okay. Now we want to verify that another function is a solution of the differential equation. It's actually pretty simple. Same question. Let's verify that y equals c1 times x to the negative 1 plus c2 times x to the first plus c sub 3 times x times natural log of x plus 4x squared is a solution of the differential equation that looks like this. You've got x cubed times y triple prime plus 2x squared times y double prime minus x times y prime plus y equals 12x squared. Okay, So if I'm telling you to verify that a function is a solution of the differential equation, I'm telling you in advance, this definitely works. Provided that there are no typos, provided this is actually a function that, provided this is actually a solution, it should satisfy this equation. So to verify that, all you're going to do is plug in this function. So everywhere you see a y, you're going to replace it with all of this. Everywhere you see a y prime or a y double prime or a y triple prime, you're going to replace it with the first derivative, second derivative, or third derivative of this. So it's just like if I were to give you x equals 0 and say, does x equals 0 work for this? We just plug in x equals 0, we see 6 equals 0, it's not going to work. What about x equals -3? Say, well, 2 times -3 is -6, and -6 plus 6 is 0, so that does work. So that's all we're really doing here. The only difference between the algebraic version and the differential equations version is you've got to compute some derivatives first. So we want to verify that this function is a solution of this equation. So we will compute y prime and y double prime and y triple prime, and we'll substitute those into the left-hand side of the differential equation. So we've got y, it's up there, and the assumption is that C1, C2, and C3 are constants. So those are just generic constants, arbitrary constants. So we have a constant times x to the -1 plus a constant times x plus a constant times x times natural log of x plus 4x squared. The derivative of a constant times x to the -1 is that constant times -1 times x to the -2. The derivative of a constant times x is the constant. Now for this one, I've got to use the product rule. So I've got, this is my first function and that is my second function. So we're going to have the derivative of the first times the second plus derivative of the second function. Derivative of the second is 1 over x times the first. So that's the product rule. So that's the derivative of the first term, derivative of the second term, derivative of the third term is those two. Drop the parentheses because we're just adding. And then the derivative of 4x squared is, of course, 8x. And of course, that x and that 1 over x reduce, and we end up with this. Okay, so we're going to need that for our y prime. We also need y double prime. Y double prime is the derivative of this piece. Well, I'm going to bring my constant down. The derivative of x to the -2 is -2 times x to the -3. The derivative of C2 is 0. The derivative of a constant times natural log of x is that constant times 1 over x. Derivative of C3 is 0. Derivative of 8x is 8. Okay, so we'll simplify this a little bit. So I've got 2c1 times x to the -3 plus c3 times x to the -1 plus 8. Next, we want to compute y triple prime. Take the derivative of this again. We've got 2c1 times -3 is -6c1 times x to the -4. And then I've got the derivative of a constant times x to the -1 is -1 times that constant times x to the -2. Derivative of 8 is 0. So I've got my y prime, my y double prime, and my y triple prime. I'm going to substitute those and y, don't forget that this is your y, into the left-hand side of the differential equation. Our hope is, after simplification, we're going to get the right-hand side, which is 12x squared. So we're going to keep all of that right here. And let's substitute into the left-hand side. So you've got x cubed times y triple prime. It's a little hard to see. There it is. Actually, I think I'll just write it down for us right here. x cubed times y triple prime plus 2x squared times y double prime minus x times y prime plus y. And all of those y's and y's derivatives are going to be substituted. Okay. Y triple prime is negative 6c1 x to the negative 4 minus 6 or minus c sub 3 times x to the negative 2. Then we're adding 2x squared times y double prime. And y double prime is right there. That's 2c1 x to the negative 3 plus c3 x to the negative 1 plus 8 minus x times y prime, which is negative c1 x to the negative 2 plus c2 plus c3 natural log of x plus c3 plus 8x. And then the last thing is just this plus y, and y is the original function. So we'll say plus c1 x to the negative 1 plus c2x plus c sub 3x times natural log of x plus x to, or 4x squared, excuse me. Now all of that is supposed to simplify. That's the left-hand side. It's supposed to simplify to the right-hand side. Now I never write equals 12x squared. I never write equals the right-hand side because I'm not actually sure that it equals that yet. So we are substituting y prime, y double prime, and y triple prime into the left-hand side of the DE. Now we just simplify. Distribute that x cubed. And remember, you want to add the exponents. So that's going to give us an x to the negative 1 here. X cubed times x to the negative 2 is going to be an x to the first. You're distributing here as well. You've got 3 terms to distribute to. So you have 4, c1, add the exponents. It's going to be an x to the negative 1, plus 2, c3, add the exponents. It's x to the first. 8 times 2x squared is 16x squared. Distribute the negative x. A negative times a negative is positive. We have c1. X to the first times x to the negative 2 is x to the negative 1. You have a negative x times c2, so that's negative c2x, minus c3x natural log of x, minus c3x, minus 8x squared. And we've taken care of all of these guys. And then the last one is just that. I'm going to rewrite it again. Okay, hopefully we've got some cancellations. So I see that those reduce, and these two reduce. I've got 2c3x minus c3x minus c3x is 0 times c3x, so those are gone. I've got 4 plus 1 plus 1, those 6 of those, and then we're subtracting 6 of those, so those are gone. And now I've got 16x squared plus 4x squared is 20x squared. 20x squared minus 8x squared is 12x squared. So we'll say since the left-hand side equals the right-hand side, that function that we came up with, y equals c1 times x to the negative 1 plus c2x plus c3x natural log of x plus x, or 4x squared, is a solution of the differential equation. Now, if you're looking for the maximal interval of existence, the largest interval where this function is well defined is 0 to infinity, because we can't take the log of 0 and we can't take the log of a negative number. So if I want to state the maximal interval of existence, and it's good habit to state the interval where that function satisfies the differential equation. That's 0 to infinity. Also, this function is undefined at x equals 0 as well. Okay, so that is how we determine, or how we show that a function satisfies a differential equation. It's actually pretty simple. All you do is take the necessary derivatives, substitute into the left-hand side. If you can show that the left-hand side equals the right-hand side, you have verified that the function satisfies the differential equation.